Hello, and in this final video about AC power, I want to talk about the power factor and power factor compensation. First of all, what is the power factor? Well, most simply put, the power factor is the cosine of the argument of the complex power. So if the complex power was represented by this point on the Argand diagram, the power factor would be cosine of theta. Now, since we know that the complex power has the same phase angle as the complex impedance of the component, this also means that the power factor is the cosine of the phase angle of the complex impedance. A power factor of 1 implies that the phase angle is 0, which means that we only have active power, we have no reactive power at all. All of the power is being dissipated and lost in heat or light, energy lost to the circuit. None of it is being stored in order to be pushed back into the circuit at a later time in the cycle. On the other hand, if we had a power factor of 0, that would mean that theta was 90 degrees, we only had reactive power, we were losing no energy from the circuit at all. All that's happening in this component is that energy is being stored and then released back into the network at a later time in the cycle. Now, from the point of view of power distribution networks, reactive power is not a good thing. Reactive power just means that there is some energy that is being pushed down a long cable from the power station generating the power to the load, which is only being stored in the load and then pushed back down the cable backwards again. It can be a long way between the source of the power and the load, and this just results in extra currents flowing down those long cables, which do have a certain resistance, and you're going to get certain losses just due to pushing currents up and down those cables. It would be much better then if our loads only ever had a real complex impedance. Then there would be no reactive power being stored here and pushed back down the cable at some later time. This is exactly the idea of power factor correction. Supposing that our load was just this resistor and this inductor in series, like it was in the last mini-lecture, but we were adding a capacitor. And we added a capacitor in such a way that the total impedance of this load, including this extra capacitor that we've just added in, is real. We would have to choose the right value of capacitor to use, but if we do that, then we could make the total impedance here look real and therefore get rid of any reactive element of the current flowing from the source to our load. Calculation can get a little bit tedious because we've got to try and make this expression here, which is the complex impedance of this network here, look totally real. We have to cancel out all the imaginary components of this expression. Well, you can go through the algebra, work out the real and imaginary parts of this expression here, and therefore come up with the value of capacitor that you need to use. But there is a slightly easier way to do the calculation. And the slightly easier way is to note that if the complex impedance of this network is going to be real, then the inverse of the complex impedance must be real as well. Well, the inverse of the complex impedance will be the inverse of this network plus the inverse of this network, because we've effectively got an RL network in parallel with a capacitor. And using the formula 1 over Z total is 1 over Z1 plus 1 over Z2 for two impedances in parallel, we would get 1 over the total impedance is 1 over the impedance of the inductor and the resistor, J omega L plus R, plus 1 over the impedance of the capacitor, which is just J omega C. If we express this term here in terms of its real and imaginary components by multiplying top and bottom by its complex conjugate, we would get minus J omega L plus R over minus j omega L plus R times j omega L plus R plus j omega C. Multiply those two terms on the bottom together. Minus j omega L plus R over R squared plus omega squared L squared plus j omega C. That's minus j omega L over R squared plus omega squared L squared plus R over this term here plus j omega C, and we want that to be real. If that's going to be real, then this term here and this term here must cancel out, which means that j omega L over R squared plus omega squared L squared must be equal to j omega C. The two j omegas cancel. We just end up with C equals L over R squared plus omega squared L squared as our final result. Still takes a few lines of algebra to go through, but I think that's an easier way of doing it than just plunging through and trying to work out the real and imaginary parts of the total impedance. We can see an example of this working in the simulator. Here I've got an alternating source feeding a load, which is an inductor in series with a resistor. And if I run the simulation, I get this. You'll see that the maximum values of the current occur at around this point here, and that produces 6.84 volts across my resistor there. And it's the resistor that's doing the useful work. It's dissipating the heat, or it's pumping fluids, or it's shining lights, or something like that. That's the energy that's actually leaving the circuit, doing something useful. So, in order to get 6.84 volts across my resistor doing useful work, I have to send a maximum of 68.4 milliamps through this network. Remember that value, 68.4. However, supposing I switch in this capacitor and I run it again. Okay, maximum value of the voltage across the resistor, about 6.72 volts. Maximum value of the current, 56.9 milliamps. It's dropped quite significantly. With the capacitor in the circuit, the maximum current, about 56.9 milliamps. And the voltage, the maximum voltage across our load occurs about there. It's about 6.72 volts. Without the compensation capacitor in the network, we have a maximum value of the voltage across the resistor, 6.72, exactly the same. But the maximum value of the current that we have to send through the network in order to get that power is 67.2. We have saved about 10.3 milliamps. Exactly the same voltage across the resistor, and therefore exactly the same amount of useful work being done by our circuit, and yet we've dropped the current required from our source from 67.2 to 56.9 milliamps. With that smaller current, any losses due to the transmission, due to small amounts of resistance in the cables between the voltage source and our load here, are going to be reduced by around 15%. which is going to save quite a lot in terms of wasted energy and potential cost due to being able to use smaller, lighter cables. It's a very popular and very common thing to do. This is an example of power factor compensation in real life. Most of the domestic electric supply, the domestic load, tends to be slightly inductive because it tends to be things like pumps in central heating systems or fridges or that kind of thing, and they tend to have a slightly inductive complex impedance. So at the electricity substation, you'll have a large capacitor block which is trying to compensate out for that inductive component in the domestic load. And these are just big capacitors stuck at an electric power station. It's kind of magic, really. You can get exactly the same power into your load by taking less current from your source, purely due to the fact that we are no longer taking extra energy at some points in the cycle and pushing it back again at other points later on in the cycle. And that brings us to the end of this series of talks about AC power.